before we go into lesson 13, let's just go down here, make some space, and let's just review what we've learned so far in terms of the formulas. So these are the formulas we've learned so far in electrostatics. The first one that we learned was Fe equals K Q1 Q2 over R squared, the electrostatic force between any two charged particles at a given distance, right? The electrostatic force between two charged particles at any given distance. Then that's a pretty straightforward formula. Then we learned this formula. Do, 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 do. And that is the electric field strength. Put this line over there. The electric field strength in a non-uniform electric field at a given distance. So, for example, I've got a charged particle right here, and then I've got a point here in space, and I want to figure out what's the strength of the electric field at that point, at that distance, that distance away from the particle. Okay, so that's the strength of an electric field in a non-uniform field created by a charged particle. Then we learned a kind of a variation of that formula, or not a variation, but we learned this formula here, E equals Fe over Q, right? And again, that's to do with the electric field, right? And this one, just to just liken it to gravitational fields, right? A gravitational field is measured in gravitational fields are measured in newtons per kilogram, and electric fields can be measured in newtons per coulomb. And then the latest formula that we learned was related to voltage, and that is that the voltage equals the change in energy divided by the charge. And again, we'll kind of review the units for that, joules per coulomb. Okay, so electric field strength is newtons per coulomb. This is joules per coulomb. Oh no, it's doing that again. And specifically, we did this for particles between parallel plates, because in a parallel plate, we have a uniform electric field, Okay, which brings us to today's topic, and today's topic is voltage in a uniform field. And the first part of your notes go to formula manipulation. So here, let's go through this. We have work equals force times distance from physics 20, which we can rewrite as that because we know that a change in energy equals work. We also know from the previous lesson this formula here, voltage equals a change in energy divided by Q. So, right, it's change in its work per coulomb. And what we can do is we can substitute the FD in for this E right here. That's going to give us this. It's going to give us V equals FD over Q. And then we also know this formula here. And what can we substitute? So in this one, we see an F divided by Q, but we know from this formula here that F divided by Q is E, so we end up with this formula here. We take out that FQ and we put in E. We end up with this formula here, V equals E over D, and on your formula sheet, that looks like this, E equals V over D. And what is that the formula for? Yes, as you've been dying to know, waiting for it all this time, that is the formula for the electric field strength in a uniform electric field. So just to remind you, this formula here is the electric field strength in a non-uniform electric field. This is for the electric field strength in a uniform electric field. Okay, where D is the distance between the locations, delta V is the voltage or the potential difference, the electric potential, whatever you want to call it, and E is the electric field. Okay, and if you look at the units for this, well, this is electric field strength, right? The units for this are going to be volts, or voltage is measured in volts, and distance is measured in meters. Right? And if you remember the units for this one here, this is newtons per coulomb. So therefore, volts meters must equal newtons per coulomb, which again seems strange. It probably seems strange in the same way that in physics 20, we said that newtons per kilogram equals meters per second squared, and that's true. They're both units of acceleration due to gravity or gravitational field strength. And this is the same thing. These do mean they are identical. Okay, if you want to prove that very quickly, then you can say, well, if I look at this formula here, V equals ED. E is measured in newtons per coulomb, and D is measured in meters. Right, so then I substitute that in right over here. Uh-oh, this is going to get a little convoluted. Let's go to green. So it's going to be newtons per coulombs times meters, all divided by meters, equals newtons over coulombs. And you can see that the meters cancel out, and you're left with newtons per coulomb equals newtons per coulomb. So just a very simple way of proving that those two units are, in fact, equal. Okay, on to example number 1. Let's erase that mess that I made first. Example number 1 says we have 2 parallel plates that are 16 centimeters apart. 2 parallel plates. You don't really need to draw a diagram, but why not? Why not? Let's make one positive, one negative, and they are 16 millimeters apart, 16.0. We want a uniform field of 800 newtons per coulomb between these plates to determine the voltage we must apply to these plates. Yeah, you really didn't need to do a diagram in this question. It's just quite a simple question. The new formula that we've just learned is E equals V over D. E equals V over D. I'm going to be lazy and leave out the vector signs and the delta signs. Just it's fine in that form there. And we're solving for voltage. So the voltage equals ED. The electric field strength is 800 newtons per coulomb. The distance between the plates is 16 millimeters. 16 times 10 to the negative 3, or 0.016. Just personally, when I see something in millimeters, to convert it to meters, I just add times 10 to the negative 3 at the end of it. Multiply those two numbers together, and you get 12.8 volts. 12.8 volts, or 12.8 joules per coulomb, if you wish. B says determine how much work you need to move an alpha particle from the negative plate to the positive plate. So let's just go back and look at our diagram. We have an alpha particle from the negative plate to the positive plate. So here's your alpha particle right there, and we want to move it from the negative to the positive. Right, we're moving it in the direction it doesn't want to go, because an alpha particle has a charge of +2. So we're going to have to do some work to move it against the grain, just like I have to do work to pick things up off the ground, working against gravity. And from that, so which formula are we going to use here? Determine how much work. We're trying to find the work. But remember, work equals a change in energy. Because if you start looking around for the formula with work in it, you may come up a little short. Work equals a change in energy. What formula do we have that has voltage in it and charge and change in energy? Yes, we have this. Sorry, we know the voltage. The voltage is 12.8. What else do we know? Let's just write down everything we know. We know the distance is between the plates is 16 times 10 to the negative 3. And we know we're dealing with an alpha particle. So as soon as you see alpha particle or electron or proton or neutron, then you know a couple of other pieces of information because they're on your formula sheet. One of those is charge. We know that the charge of an alpha particle, it has two elementary charges because it's two protons and no electrons. So 2 times the elementary charge, 1.6 times 10 to the negative 19, is 3.2 times 10 to the negative 19. Okay. You also know from your formula sheet the mass. Where is it? Where is it? Right there. The mass of an alpha particle is on the back of your formula sheet. So I'm going to have to change this. And the mass of an alpha particle is 6.65 times 10 to the negative 27 kilograms. Okay, so I'm writing all this information down so that you know exactly what you have, and then you can pick a formula that has these things in it. And if we're looking for this, and we have this, and we have this, then we have a formula. The formula is voltage equals delta E over Q. We are solving for delta E. How much work do you need to do? So it's just VQ, the voltage times the charge. Oopsie, oopsie, oopsie. That should be 3.2 times 10 to the negative 19. And that's going to give you an answer of 4.10 times 10 to the negative 18 joules, because it's work or energy. All right, and the last says explain if this energy is kinetic or potential. Well, if we go back to our diagram, we have to do work against the field, against the force of the field, I guess I should say, and therefore it's going to be potential because now this alpha particle, this positively charged alpha particle, is sitting against the positive plate, and therefore it has lots of potential to do work. If you let go of it, it's going to accelerate towards the negative plate doing work in the process. And so the answer for that question is potential. You can just circle that. Okay, how are we doing for time? Should we split this up into, let's do the next number 2, and then, oh no, we'll just do it all. Just be one long lesson. Conservation of energy in a uniform field. You can do a lot of questions if you keep in mind the conservation of energy. So when we're moving particles around fields, they're gaining potential energy and losing kinetic energy, or vice versa. They're gaining kinetic and losing potential energy. The majority of these questions involve electrons, so keep in mind that you have the mass and the charge of an electron, both on your data sheet. And then it talks about, you could also be asked questions about alpha particles. So example number 3, an electron is accelerated from rest between two plates 4 centimeters apart from each other. The voltage between the plates is 20 volts. Determine the velocity of the electron when it reaches the plate. So again, let's write down all the information we have. We have the distance between the plates, 4 centimeters, 0.04 meters. We have the voltage, 20 volts. And as soon as you see the word electron, you know that you have the charge, and you know that you have the mass. And the mass of an electron is 9.11 times 10 to the negative 31 kilograms. So it's pretty light. What are we trying to determine? We're trying to determine the velocity, lowercase v equals question mark. Now, when you're dealing with these type of questions, particles in charged particles in electric fields, we're dealing with energy, specifically kinetic energy. So what formula has velocity and kinetic energy in it? And that, of course, is the formula EK equals 1/2 mv squared. So in other words, what we're saying is eventually we're going to use this formula to calculate the velocity. But first we need to calculate the kinetic energy. And it says an electron is accelerated from rest between two parallel plates. So in other words, it was all potential energy, and all that potential energy was converted into kinetic energy. Right? You have two plates here. This one's positive. This one's negative. Here's your electron. It is accelerates towards this one from rest. So its initial kinetic energy is 0, and then accelerates towards the plate, and all of the potential energy that it has when it's at this point here is turned into kinetic energy. All right, and now what formula do we have that we can calculate the change in energy? Well, we have voltage and we have charge, so therefore we can use our voltage formula. Step 1, we can calculate the change in energy using the voltage formula. The change in energy equals the voltage, which is 20, times the charge, which is 1.6, times 10 to the negative 19, and that's going to give you, that should be too hard, 3.2, times 10 to the negative 18 joules. Okay, so we've got the change in energy, and we know that that change in energy is all potential to all kinetic. Right, so now it's all kinetic energy, and then we can just substitute into this formula here to solve for the velocity. And I am going to run out of room, so I'm going to have to write this really small because there's a problem with the smartboard, and it's doing this. Yeah, it just stops there. I don't know what happened. So I'm going to have to write this really small. EK equals 1/2 mv squared. We rearrange this formula for velocity. You should remember this in Physics 20. If you don't, then here it is. The velocity equals the square root of 2 times EK divided by m. So look at that. We're going to need to use the m. The only thing that we don't need to use so far is the distance between the plates. Plug in your numbers. The square root of 2 times 3.2 times 10 to the negative 18 divided by the mass. Oh my. Lucky we got different colors here. The negative, yeah, look at that, Oh, that drives me bonkers. And then put that into calculator. Make sure you're using the E key for scientific notation to make things easier, and you will end up with the answer of 2.7 times 10 to the 6th. The 6 meters per second, which if you ask yourself, is that slow, fast, medium? It's super fast. It's incredibly fast. And those are the kind of numbers we're going to be dealing with when you put electrons, something as small as an electron, in a magnetic field, or sorry, in an electric field. And then where are we here? I just realized that I missed a question. Yep, I did. I missed number 2. Okay, well, it doesn't matter. We're going to go do finish number 3 here, and then we will come back and do number 2. Okay, so B, you've calculated the maximum velocity for this situation where the electron has accelerated all the way from the negative to the positive, going through the entire potential difference. Determine the electron's velocity when it is only moved 1 centimeter away from the negative plate. Okay, so this is definitely a thinking person's question. Right, here's our plates. How are we doing? Oh, we're almost at 20 minutes. We're almost at 20 minutes. I'm going to stop, actually. I'm going to stop. I'm going to do this in the second part just so you can take a breather, because 20 minutes is a long time to watch a video, for me anyway. Unless it's like Alita Battle Angel, then it doesn't goes much slower. You know what I'm saying. It's a good movie. I liked it. Stop.